So we are going to start with the stereoisomerism in coordination compounds, right? So as far as the discussion goes, we need to discuss three geometries. Okay, this is which geometry? Aisha, Marwa, Jaslin, can you tell me? This is which geometry? Which arrangement? You can clearly see that this arrangement is, it is the square planar arrangement. Got it? Is it clear or not? And this is tetrahedral. Got it? And octahedral. Right? So what do you understand by stereoisomerism? First of all, tell me. And how many different types we need to look into when we discuss stereoisomerism? Just tell me quickly. This is octahedral geometry. Okay. So stereoisomerism, we have two kind of stereoisomers. One is the geometrical isomers and another one is the optical isomers. Okay. So how many different kind of geometrical isomers are there? Any idea about it? What do you mean by stereoisomers? First of all, tell me that. Yeah. Aisha, Marwa, Jasleen, am I audible?
Yes, sir.
Okay. So what do you mean by stereoisomers? So two isomers, they have the same formula, but they have the same groups. Okay. But the three-dimensional arrangement is different. They differ only with respect to the 3D arrangement. Is it clear? That is stereoisomer. Same formula, same groups or atoms, okay, but having different 3D arrangement. And there are two types we need to consider. One is the geometrical, another one is the optical. Geometrical isomers and optical isomers. Is it clear or not? So geometrical isomers, how many types of geometrical isomers are there? What do you mean by geometrical isomer, Aisha?
Sir, cis and trans.
Yeah, cis and trans means if the groups are locked on the same side of an atom or of a double bond in alkenes. Okay, in organic we look for alkenes, right? If the groups are locked on the same side, if they're present on the same side, there that isomer is known as cis. But if the same groups are on the opposite side of an atom or a double bond, that is called trans isomer. Okay. So geometrical isomer is cis and trans isomerism. Okay, that is the most simplest way, right? And square planar complexes, the tetrahedral, it cannot show geometrical isomers. Can you tell me why? Who all can show geometrical isomers?
So heteroleptic coordination compounds.
Yeah, heteroleptic, that is very important point, very good point. Yes, exactly. Heteroleptic. And so, but I'm talking about the geometry. Which geometry is capable of showing geometrical isomer? And we are having most three common geometry, that is square, planar, tetrahedral, and octahedral. So geometrical isomerism is exhibited by square planar complexes and octahedral complexes. Is it clear? It is not exhibited by tetrahedral. Marwa, is it clear? Why tetrahedral cannot show geometrical isomerism, Jesleen? What's the reason? Marwa, Aisha, tell me. What's the reason why tetrahedral cannot show geometrical isomer? Square planar and octahedral can show geometrical isomers.
So because of the positioning of the atoms, the relative position,
So yeah,
they're
because
the
it is a
same.
symmetric. Yeah, it is a symmetrical. All four ligands are symmetrically placed. Okay, so there is no tetrahedral or no cis or trans possible. Cis means two groups in a same plane on same side, right? That square planar, you can clearly see that two groups are on the same plane. They are on the same side or on the opposite side of the metal. Okay. Same in the octahedral, you can also see. But tetrahedral, you cannot have that kind of cis and trans arrangements. Is it clear? So square planar complexes and octahedral complexes can exhibit geometrical isomerism. Next is let's compare the square planar complexes. And very correctly you said that you need a heteroleptic complex to show geometrical isomerism. For example, in if we have all same ligands, then it is not going to be cis or trans. Okay. This is a complex with all four ligands equal. If I try to draw it, this is a square planar complex. So it is the platinum. There are NH3 groups. Okay. There are NH3 group, four NH3 groups are there. Okay. And if we try to interchange them, there is it will not result into any new isomer. It is because all four groups are same. If they are same, you cannot have, even if you change, it doesn't matter at all. So how many geometrical isomers are there? for this? Yeah, Marwa, can you tell me? How many? Zero. It cannot have cis or trans. This clean, is it clear? Aisha? So you need to have heteroleptic complex, okay, to exhibit geometrical isomerism. That is a very important part. The next thing is, suppose if I change one of the ligand and if I take one ligand different from rest of the other three ligands. So let's look what we have. Platinum is +2, Cl is -1. So the total charge is going to be +1. So you can see here how it is going to look like. So if I interchange the position of Cl and NH3, is it going to exhibit a geometrical form, a new geometrical isomer? If it is going to exhibit a new form, a new geometrical isomer, then I should say that it will show geometrical isomers. Otherwise, I should say that it is not going to show the geometrical isomer. So what do you feel?
So it's showing square planar, right? The structure.
It is a square planar complex. Yeah, DSP2 hybridization. So if I interchange any NH3 with the Cl, are we going to get a new isomer?
No, so
Let
no,
Yeah,
because
it is just going to be the same. Okay.
some
How you know? Okay, don't compare it in our frame of reference. Okay. So just check who is around, who is on the adjacent of Cl in this case. Adjacent, that means at 90 degree. You have two NH3 groups. Is it clear or not? This is NH3, this is NH3, and who is on the back side of the Cl? That is also NH3. Is it clear? And if I change this Cl and if I put it here, then also it is going to be the same thing. Got it? What's there on the either side of the Cl? The two NH3 groups. And on the back side of the Cl, you still have the NH3. And they are same, just if you flip it like this, it is that Cl is going to come down and NH3 is going to go up. It is not a new isomer. So number of geometrical isomers will be equal to 0. Is it clear? Now we are having a very important example because that is the example which can show geometrical isomerism, and we also discussed it in the applications of coordination compounds, and that is the compound that is a complex of platinum which is used as a medicine. Okay. What is the name of this molecule? Just try to recall, we have discussed it in the coordination compound. chapter? Tell me quickly.
Cisplatin.
Yeah, cisplatin and transplatin, exactly. Yes. So cisplatin was used as an anti-cancer drug. We have seen. So cisplatin and trans means this is the one which is going to show the geometrical isomerism. This is cis. Why it is called cis? The reason is clear once you see the position of the two Cl atoms, and why the other one is known as trans. That also is quite clear by looking at the position of the two Cl atoms. Is that clear to everyone? Aisha, Marwa, Jesslyn, tell me quickly. Is it clear or not?
Yes, sir.
So
Clear.
if you just try to uh, cover platinum by your hand, you can see that both the Cl are on the same side. Okay, and if you this look at the platinum, the Cl are across the platinum at 180 degrees. Okay, in this case it is the 90-degree bond angle, and that case they are opposite, exactly opposite, means 180 degree. So that is going to be the trans, and this is going to be the cis. Cisplatin and transplatin, we have discussed that they are used, the cisplatin is used for the treatment of cancer. So I hope this is clear to all of you. Okay, cis and trans, okay, 90-degree, two same, but you need to have at least two ligands of one type and two ligands. It should be heteroleptic, and two ligands of one type and two ligands of another type. Then only you can consider it to be the uh, complex which can exhibit geometrical isomerism. Otherwise, if it's just one ligand different from rest of them, it is not going to be geometrical. Okay, just, and if all ligands are same, then also surely it is not going to be the show the geometrical isomers. I hope this is clear to all of you. Okay, now let's say suppose if we have uh, maximum what you can do, how many ligands you can change in a square planar complex. How many different type of ligands you can take? Maximum you can take all three or four ligand to be different. Is it clear or not? So
Yes, sir.
suppose if I take platinum and if I take all four ligand to be different, okay, let's call them for the sake of ease, instead of writing the actual formulas, I will write it just A, B, C, D. Small letter represent different ligands. Okay, so for example, this is one of the complex A, B, C, and D. So how many different arrangements we can have? Okay, first what we can do is you can choose any two ligands. Okay, so this is, I hope it is clear to you what which type of complex I'm trying to show. I'm trying to show a square planar complex with all four ligands to be different. Okay. Example, I can write one example. Example, suppose if you have platinum, Cl, Br, H2O, and NH3. You can see that there are four ligands and they all four are different: Cl, Br, H2, NH3. Instead of writing the formulas, actually, what we can do is we can just I have representing them. I am representing them by ABCD. Okay. So how many different isomers we can have? Let's try this one. This is a very important question. It is a square planar complex with all different ligands. Okay, how many geometrical isomers? You can just write them ABCD. Very important question. I hope the question is clear to all of you. Yeah, Marwa, how many are you getting? How many different arrangements, cis trans, different types of ligands you can have? If you have all four ligands found to be different, any idea? Jasleen, any idea? Aisha, how many are you getting?
So 3.
Yes, three, exactly. So what we can do, we can choose any two of them. Like for the sake of convenience, I can choose A and B. And you can see that A and B are at 90 degree. They are cis right now. Make them trans. This is going to be different from the first one. Okay. And if you don't want to make them trans, you can keep A and B as cis, but you can interchange C and D. If I interchange C and D, will it create a new isomer? Let's see by drawing it. A and B and C and D. C, I have put it on the left hand side and D on the right hand side. Look, this is a new isomer. Why? Because in the first isomer, A and D were at 90 degrees and A and B were also at 90 degrees. A was cis with respect to B and D, but A was trans with respect to C because A and C were exactly opposite to each other. Now A and D are exactly opposite to each other, so it is a new isomer. So just remember it because sometimes due to examination pressure you may forget it. Okay, just remember that you will have three isomers. Okay, in a square plan complex where all ligands are different. Is it clear or not? Any doubts on this? Do remember this. So how many isomer? Three. Okay. Now the next thing is let's move on to the octahedral complexes. Let me write geometrical isomerism in octahedral complexes. First of all, I would like to show you that which positions are cis and trans, which positions to be considered as cis and which positions to be considered as trans. And that is very simple. Suppose if I take these two positions, are they cis or trans? The two positions which are marked by circles. Any comment about this arrangement? Tell me quickly. Is it cis or trans? Aisha, Marwa, Jasleen, tell me. What is the angle? This is 90 degrees. Okay. So they are cis. Okay. And what about this position and this position? The positions which are represented by two cross, that also is 90 degree. Getting my point or not? That is also
Yes, sir.
cis. So do we have transposition in octahedral complex? Tell me quickly. Yes or no? Do we have any transposition in octahedral? The answer is yes. The transposition will be this one. The positions indicated by two tick marks, right? And what is the angle between these two positions? The one which is up and down. It is 180. 180 degree means opposite, exactly opposite. Or this one and this one, right? That also is exactly opposite. That is 180. This position and this position, they are also 180. So I mean to say here is, if you have two groups at 90, that is going to be cis, and if they are at the opposite position, that is going to be trans. Is it clear or not? Cis and trans arrangement. Any doubts on this? This is a general way of showing the cis and trans on the octahedral geometry. But now we need to work with individual ligands. Okay. Specific examples, right? So I am showing the three octahedral complexes of cobalt. The first one is having all six ligands same. It is a homoleptic complex. So how many geometrical isomers will be there? For the first one, Marwa, tell me. How many? Will it show geometrical isomerism? Yes or no? No, it will not show. Why? What's the reason? It will not show because all are same. All 6 ligands are equal. Okay. So whom do you call cis and whom do you call trans? Is it clear?
Yes.
So there are 6 ligands. You can change or do not change. It doesn't matter at all because all 6 are same. Okay. And so whom do you consider cis, NH3 and trans NH3? Everywhere you have the same ligands. So you cannot change them and make a new arrangement possible. That is not possible for you. So no geometrical isomers. Is that clear? Suppose if you have just one ligand which is different from rest of the 5 ligands, the second case. Got it? So can it show geometrical isomerism?
No, sir.
No. Why? Because you have just one signal. You need to have at least 2 groups for the sake of comparison, which you can call them as on same side. 2 groups are on the same side or 2 group on the opposite side of the metal. Okay, just one group. Okay, that will not show geometrical isomerism. And this is a very important example because in octahedral complex, this is the complex which is having at least 2 ligands different from rest of the 4 ligands. This can exhibit geometrical isomerism. So let's look like this. It like this. Let me draw it. There are 2 chlorine chlorido ligands. You can put them in a cis manner or you can put them in a trans manner. Is it clear or not? This
Yes, sir.
one is going to be cis or trans. The one which I have just written. Is it cis or trans?
So cis, because
Yeah,
the
it is.
CL is 90-degree apart.
Yes. Yeah, 90-degree it is there, that is cis. Yes. Normally, this is the way to represent cis. But there are other ways also. For example, this is also cis. Okay. But this normally, if you get it in the form of questions, don't get confused because it is bit confusing because one ligand is up and another is in the plane. You may not be able to recognize it very quickly that it is cis. The one which I wrote earlier, that was actually more easily recognizable. This one, okay, that one was more easily recognizable because you can clearly see that the two CL are written side by side and they are cis. But if they are written one CL up, another in the horizontal plane, check the angle. If that angle is 90-degree, it is cis. And what about this one? This is the most convenient way of showing a trans arrangement where you put one ligand at the top another at the bottom. But not only the top and bottom, you can put them like this also. One here at 180 degree. You can choose any two positions which are at 180 degree. Is that clear to everyone? And that can give you cis and trans arrangement, right? Clear?
Yes, sir.
So this is the very important example because this is the first example which can show cis trans isomerism in octahedral complexes. Okay, now let's try with. Till now, I have taken two ligands. At least two ligands should be of one type and other four should be different. Okay. In order to exhibit geometrical isomerism, and this is going to have two geometrical isomers. Got it? Cis and trans. But what will happen if you have three ligands of one kind and another three of different kind? Can it exhibit geometrical isomerism? This is a very, very important case. So this is the cobalt in the central metal atom. You have three chloride and three amine. Three ligands of one type, another three of another type. So just try to figure out how many geometrical isomers will be there. Just try to draw it and tell me. Aisha, Marwa, Jesslyn, just quickly let me know. Now, Jesslyn, am I audible? Aisha, Marwa, how many are you getting? This is an octahedral complex that we know because there are 6 ligands. Got it?
Two.
Yes, 2. And how to draw them? So what should I put over here in this place? Cl or NH3? Let's say suppose
Cl.
if I put Cl, pardon?
Cl, sir.
Okay, Cl. And what you have put here?
NH3.
NH3, okay. In this place, yeah, first tell me this one.
NH3.
NH3, okay. At the bottom position
Cl.
is Cl, okay. This one,
NH3.
NH3. And the last one will be Cl, okay, because we have 3 Cl. Okay, this is one of the isomer, right? How to draw the another isomer? What should I put at the top? Means how you have drawn it, just I wanted to know that. This is one isomer, that is absolutely correct. But how you have drawn the other isomer? What should I put at the top?
So NH3.
NH3, okay. And this one?
NH3.
This one
Cl.
is Cl.
NH3.
NH3, okay. And then you have Cl and Cl. Got it?
Yes.
But both of these are same. They are identical. If we look closely, we come to realize that they are exactly same. This is not a new isomer. Why it is not a new isomer? Because if you compare the angle, okay, though 3Cl may appear like this or like this or like that, okay. So that appearance can be deceptive, right? You need to look at their relative positions, okay. So in the first molecule, if you try to look, the 3Cl are like this, so there is 90-degree angle and there is 90-degree angle. If you twist it, it will become this. This is also same, that the angle made by the 3Cl atom among themselves is 90 degree. Is it clear or not?
Yes, sir.
Got it. So 90 and 90, so that is also 90. Okay. It may appear different, but they are not different. They are exactly same. It may appear different because in the left hand molecule, the Cl are going toward the back side. And in the right hand molecule, they are in the flat. Okay. So let me tell you very important trick to know whether they are same or different. Okay. And that trick is going to help you to name them also, right? So just try to connect the three ligands which are identical to each other. Can you connect them? Okay. And let's try to connect the other three ligands. Why I'm using some different color. Is it clear? Maro and Jesslyn, can you see what I'm doing? Let's try to connect Aisha here also, the three NH3 groups. Got it? And the chloride, same type of ligand are being connected by lines. Got it? So you can see either you will have this kind of line or this kind of semicircular line. Got it? And you see such lines on our globe. Okay, latitudes and longitudes. You know that, right? So that's why is known as meridional. Is it clear or not? Marwa, have you understood what I'm telling?
Yes, sir.
This is the full name. Normally you call it MER, meridional. We have that Greenwich meridian, right? That is the for estimating the time at different places. So if you have three ligands of the same type, try to connect them together. Aisha, I hope it is clear. So why they are same, both are meridional. Got it? So what will be the other isomer? The other isomer will be known as facial. And how it will look like? Hmm. Is it same or different, Aisha?
Different.
Yeah, it is different. If you try to connect the two all the Cl atoms, they are not forming a semicircular latitude or longitude kind of line. They are forming a triangular face, okay, of an octahedron. Same is the case with the NH3 also. Jaslyn, is it clear or not? Marwa, is it clear?
Yes, ma'am. Yes.
So very basic, very important facial and meridional. But that facial and meridional is that these are isomers, geometrical isomers, because the formulas are same. Okay, you are not changing the groups. The groups are 3Cl and 3NH3. The groups are exactly same, but the three-dimensional arrangement around that atom is changing. Okay. If you have two groups of one kind and remaining of other kind, you can call them cis and trans isomers. And with the cis isomer have the same groups on the same side, and the trans having same groups on the different sides. Okay. But if you have three of them are of one type, another three of different type, then you have facial and meridional. These are the two isomers. So facial will have the three Cl atoms or the three ligands which are same on the same face. Okay. And in meridional, when you put the three same ligand and you try to connect them, you will observe a semicircular lines being formed. Got it? Is that clear to everyone? Any doubts on this? Now let's move on to bidentate ligands. Got it? Bidentate ligands are also connected. It is not always that you will have monodentate ligands. Okay, you can have bidentate ligands also. Complexes containing bidentate ligands. Got it? So bidentate ligands are connected by two bonds to a metal atom. Got it? It is like, what do you mean by En?
Ethane 1,2 diamine.
Ethane 1,2-diamine, it is a bidentate ligand, okay? Or you can have this as a bidentate ligand in a square planar complex. PTENCl2, this is a square plane complex. One bidentate ligand is going to take the place of two monodentate. Clear? So first tell me how many geometrical isomers will be possible for this one. You have one En, gasoline, which is a bidentate ligand, and Aisha, you have two monodentate ligand. Got it? How many geometrical isomers you can have? Aisha, Marwa, Jaslin, tell me quickly.
Sir, I didn't understand the question.
Total number of geometrical isomers. Cis trans isomers. Got the question?
Yes,
First, try to
sir.
understand the question. That is very important. Okay. Have the clarity about the question. So tell me, how many geometrical isomers you can have for this square planar complex where you have one bidentate ligand, ethene 1,2-diamine, and two monodentate ligands. Got it?
Sir, two. If we place the Cl2 adjacent, we get 90 degree, and then if we place it opposite, it'll be 180 degrees apart.
Yeah, that's what theoretically we think. Yes. So that is the way in which we are doing it till now, right? So the way which you adopted is okay, but actually we need to see that it is possible or not. Okay. But the method which you have adopted is correct, right? That is absolutely correct. This is ethene 1,2-diamine. This is a square planar complex. You can see you can demarcate the boundaries by dotted line, and two Cl are there. And this is cis, okay? And this is what you said, how will be trans, right? Cl. But there is one problem, Aisha, that trans cannot be there. Why? Why it cannot be there? The trans isomer. What's the problem? Where are we lacking? Look, the problem is not with the Cl. It is with the ethane 1,2-diamine. Can you see that if you put it in the trans, will it be able to connect? Because the ring is going to be very big. Getting my point or not? Is this ring possible? Aisha, Marwa, Jesslyn, tell me. Is it possible or not?
No, sir.
Though I have drawn by drawing a bigger line. Okay, you can see. But practically, we know that it is not possible because that distance is going to be very large, and it will not be possible for the ligand to connect the problem is not with the Cl. Okay, are you getting my point? The problem is with respect to the bidentate ligand ethane 1,2-diamine. Got it? That is the actual problem, and you cannot connect in a trans manner. So it is not going to show cis trans isomerism, so number of isomers will be 0. Is it clear or not? So just try to understand that if you have a bidentate ligand, never connect it, the two ends of the bidentate ligand, in a trans manner. Is it clear? Marwa, is it clear or not? Aisha, Jaslin, is it clear?
So the bidentate ligands, they occupy both the adjacent side.
Yes, cis positions, exactly. Because if you put connect it in a trans manner, its ring is going to be bidentate ligand is will form a ring, cyclic ring, and its ring is going to be too large to connect in a trans manner. Is it clear? Okay. So this you should keep in mind not only for this, okay, for other complexes. Never attach a bidentate ligand in trans position. Okay. Is it clear or not?
Yes, sir.
Okay, great. So it is not going to show. Theoretically, we have made, okay, but practically, when you try to look at the arrangements, you will realize that it is not possible. Okay, so 0. No geometrical isomerism is possible. Now, what about this one? This octahedral complexes having all three ligands as bidentate ligands. All the three ligands are bidentate. For example, if you try to look at the EN, all the three EN are bidentate. Can you see? This is another very important example. So how many geometrical isomers will be there for this?
So no geometrical isomers because three ligands are identical.
Yeah, three ligands. Yeah, that is that normally till now we were doing the same thing. Yes, exactly. But we need to check. Okay, once more. The geometrical isomerism is not going to be there at all. Okay, because because all are same. The points, okay, are exactly same. Ni, if I try to draw them, NH2, NH2, that is absolutely correct. It is not going to have any geometrical isomer. NH2, NH2 and NH2. Now let me connect them all. How are we going to connect them? While making the connection, do keep in mind that never connect the two NH2 groups like this. Is it clear or not? Don't connect them in this manner, because that again the same thing, the problem is going to come up, right? Always connect them in a cis manner. Is it clear? But all are the endpoints are all NH2, and if we even if we swap them, it is not going to create any new arrangement. So all same, no geometrical isomers. Got it? What about, so suppose, because till now we, and it was homoleptic also that we discussed. So let's remove one EN and put two Cl. So our formula is going to become NiEN2 Cl. Got it? Is it clear or not?
Yes.
So now tell me, is there any possibility now for formation of new isomers? Are they possible now? Well, now we are a bit more hopeful than the previous example above it, because this is a heteroleptic complex. Got it? So this I hope is clear to you. Okay. So tell me quickly.
So we can form a cis isomer.
Yeah, cis and
Cis.
trans, and we are now we are hopeful, and with the two chlorine atoms, the two chloride ligands, and they are independent to be placed in cis and trans position, because they are not connected like bidentate ligand. Got it? Is it clear or not? So we can draw them. Let's try to draw the cis one first. This is cis isomer. Marwa, is it clear or not? Jasleen?
Yes, sir.
You can see the two chlorine, they are on the same side. Okay. And now we can draw the trans isomer. Better draw the two chlorine in the opposite direction at 180 degree. Okay. But be careful while attaching these NH2. Okay, we know that we can't attach the NH2 in a trans manner. So this is one ligand. Okay, and the NH2, both the NH2s are connected on the same side, and this is another. Is it clear? And this is going to be trans. This is going to be cis. Got it? Any doubts in this? Is it clear? Cis and trans. I can demarcate the boundary of the octahedral complex. This is four groups are in the plane, and one is at the top, another is at the bottom. Got it? This I hope is clear to all of you. Okay. So we can have cis-trans isomerism in this. Okay. Very, very important question. Okay, and I hope you will be able to do it. Now we need to look at optical isomerism. So what are optical isomer? Tell me. What are optical isomers? They are a type of isomers which are stereoisomers. They differ with respect to 3D arrangement. Okay. This is true for all the stereoisomers. And I hope all of you agree with it, right? But what's the difference then? What's the difference? Even the cis-trans isomer were also having different 3D arrangement. Okay. And why the name optical is there? In the organic
So
also we have studied. Yeah, tell me first.
this is show them like they show mirror of each other.
Pardon?
They show like the
They?
mirror image.
Yeah. And when you try to put them in the polarimeter, just a second. Okay, polarimeter is an instrument which is used to check whether a compound is optically active or not. Got it? Let me show you one very important thing how the polarimeter work. Okay, just a second. Okay, so polarimeter is used to detect whether these are optically active or inactive. Got it? So just a second. These optical isomers are those isomers which show different values of the optical rotation. Okay. So just a second, let me share the screen and this is the internal setup of a polarimeter. Can you see? And these are the, can you see the light waves moving from the left hand side in different plane? And they get filtered out. Only the light moving in one particular plane is allowed to pass through that polarimeter. I hope all of you can see. Marwa, Jesslyn, can you see this? Aisha, can you see it?
Yes, sir.
And this is known as the light coming out on the right hand side, the red colored wave light. Okay, this light is represented by a wave. Okay, because it is an electromagnetic. This is known as polarized light, and it is passing through the vertical plane. Okay, and this is the polarizer filter which we are having in the polarimeter. Got it? I hope this is clear. Okay, so just let me stop the camera so that you can see it more clearly. Right, so this is the polarizer filter, polarized light. So optical, and this, when you put the compound and when you pass this polarized light through compound, optically active compound, this these light waves get tilted. Okay, the plane of polarization get tilted. So such compounds are known as optically active compounds. Is it clear? So have you understood what do you mean by plain polarized light? Is that clear to everyone? And this plain polarized light, okay, is the is the is generated in a polarimeter equipment which is used to measure whether a compound is optically active or not. So suppose if you have a compound, okay, for whom would you would like to detect whether it is optically active or inactive? Organic or inorganic compound, okay, the compound which you need to analyze, and this is the polarized light, okay, which is coming. This is the plane of the polarization, okay, vertical plane. And if you pass this light through organic compound, if it is optically active, this plane of polarization is going to tilt like this or this. Got it? Are you getting my point? If it is plane of polarization is rotated, then that compound is optically active compound. So optical isomers have different optical rotation. Okay, those compounds which show different optical rotations, and how the value of optical rotation is checked. They are checked in the polarimeter. Okay, this equipment is known as polarimeter. Yeah, just could you read it out for me, Aisha? What are optically active compounds? Am I audible?
Uh, yes, sir. Optically active compounds will rotate the plane polarized light either in clockwise direction, detro- detrorotatory,
Dextrorotatory,
or they can
okay.
rotate in
Or you can call them by small d, right? Or they can rotate it
dextrorotatory.
in, hmm, or they can rotate it in anti-clockwise direction. If they are optically active, that plane polarized light you understood. Marwa, have you seen that wave which is rotating in one plane, which was oscillating in one plane, the light waves? Okay, that is called plane polarized light. So if it is passed through optically active compound, it can either get tilted like this, that wave plane of the wave, or like this. Got it? If it get tilted, it is optically active compound. So optically active compound is the compound which rotate plane of polarized light. I am quite sure you are all aware of this, okay? And there are two types, either dextrorotatory and levorotatory. Is it clear? Okay. So optical isomers have same formula but different 3D arrangement, and they show different optical rotations when checked through polarimeter. Is the definition clear to everyone? Marwa,
yes.
Jasleen, tell me, very, very important. The same thing is going to be applicable in your organic chemistry also. Okay. Now, suppose if they can be so optical compounds can be mirror images or they can't be mirror images. Okay. So optical isomers, how they are checked. So what are optically inactive compounds? Can you tell it by reversing the definition? Optically inactive compounds are those compounds which do not rotate plane of polarized light. Got it? So when they are put through the polarimeter, the light is passed through that compound and it is going to come out as it is without getting affected. Got it? So optical isomers are compounds which show different optical rotation. They could either be mirror images of each other. Mirror image isomers are known as enantiomers. Or there could be another type of optical isomers which are not mirror images. And they are known as diastereomers. Is it clear? The same thing you are going to write it in your organic compounds also. Okay. Is that clear or not? Aisha, Marwa, tell me quickly. Jasleen,
Yes, sir.
is it clear? Very, very important. Okay. So how we are going to check whether a compound is optically active or inactive? This is the plain polarized light. Okay, this we don't have to, this is the setup is there, that whole equipment. We just need to put that compound in a glass tube. Okay, and need to switch on the lamp and need to check whether the light plane of polarized light has been rotated or it is just the same. If it is just the same, it is optically inactive compound. If it gets rotated in the clockwise direction, that is dextrorotatory. Okay, and if it rotates in the anti-clockwise direction, then it is levorotatory compound. Okay, so optically active compounds can be either dextrorotatory or they can be levorotatory. Okay, they could be there. The isomer dextro and levo is because of the mirror images. Suppose there could be optically active compound which are mirror images of each other. So those isomers, if you see their structure, they are mirror images. They are known as enantiomers. So enantiomers, if you check, both are optically active. One of the isomer will be dextrorotatory, and its mirror image isomer, because there are two isomers, is going to be levorotatory. Got it? So you need to check through polarimeter. Got it? Polarimeter can help us to make out whether the compound is optically active or not. It doesn't affect the plane polarized light, it is optically inactive. If it rotates the plane of polarized light, then it is optically active. If it is rotating the plane of polarized light, then the question arises is it rotating the plane of polarized light in the clockwise direction, or is it rotating the PPL in the anti-clockwise direction? If it is rotating in a clockwise direction, then it is known as dextrorotatory compound. And if it is rotating in an anti-clockwise direction, it is known as levorotatory compound. Sometimes optically active compound having just one formula can exhibit two types of optical rotation. One is dextro, another is levo. Okay, so why that happens? It happens because that compound is present in two mirror image isomers. Okay, one will be dextro, another is going to be levo. Is it clear or not? So in the next class, we are completing this chapter. Okay, and we can start with aldehyde and ketones, right? Because that is going to be a long topic, very important. Aisha, Jesslyn, Marwa, is it okay?
Yes.
Sir,
Yeah, we can start with aldehyde and ketones after finishing this optical isomerism. The theory already I discussed. Yeah, Aisha.
sir, can we do amine? If it's okay.
Yeah, amines. Yeah, okay, we can do amines also. Not a problem. That is a small chapter. Yeah, not linked to this. Okay, we can do amines. Okay. So I hope that is okay with everyone. Jesslyn, Aisha, and Marwa. Amines we can do. Okay.
Okay, sir.
So because that is a small topic and very important, different from all of these, and we can do it independently. So next class we are going to complete this optical isomerism, and we are going to start with amines. Okay. So let me end the class. Okay. Bye bye. Take care. Good night, everyone.
Thank you, sir.
Okay. Good night, everyone.